In this we will see exercise problems, solved problems and homework problems from polars of ellipse and asymptotes of hyperbola. So the first example what we have is chords of the ellipse touch this ellipse and we are asked to find the locus of the poles. So locus of poles is asked, so we'll have to take x1, y1 to be the pole of PQ, a chord of the ellipse which touches the ellipse. So with respect to the given ellipse, there is a standard one, x square by a square plus y square by b square equal to 1. We have to consider the polar and that touches the second ellipse. So a condition is if we have y is equal to mx plus c, then c square is equal to a square m square plus b square is the condition. So we'll have to make use of that and dropping the suffix we get the locus. So that is the idea. So let x1 y1 be the pole and then x polar is xx1 by a square plus y1 by b square equal to 1. We write that in the form y is equal to mx plus c. So you have y is equal to mx plus c. When you rewrite this thing, you will have y is equal to mx plus c. So this is the form and so the condition will be c square is equal to this touches this ellipse. So in that case what we have is c square is equal to alpha square m square plus c square is equal to a square m square plus b square. So here in the place of a you have alpha, in the place of b you have beta. So this is the condition and already c is known and beta square is because of this one. Okay, so you have this. So c square is equal to alpha square m square plus beta square. Then you'll have to divide because in order to bring it to the standard form we are dividing throughout by this. So by dropping the suffix you get the locus. Now a chord PQ of an ellipse subtends a right angle at the center of the ellipse. So that is given to us. Then we are asked to show that the locus of intersection of the tangents at P and Q is some other ellipse. So we are given an ellipse. And we are going to consider a chord PQ and the tangents at this and this point. Okay, we'll have to consider this is a P and this is Q. And we shall take this point to be say some p of x1 t of x1 y1, the locus of which we are trying to find. And if we have to find the locus of any point, then some condition is to be given. So the condition given is the chord PQ subtends a right angle at the center of the ellipse. Center of the ellipse is nothing but C of 0, 0. So this chord now we have to consider, and the ellipse is known to us. By homogenizing the ellipse with the help of this line, we get the combined equation of the lines through origin, pair of straight lines. So that because it subtends 90 degrees, coefficient of x square plus coefficient of y square will give us equal to 0. Dropping the suffix we get the locus. So that is the idea. So how we can get the equation of PQ? So for that only he has given the tangents at P and Q intersect at say T of x1 y1, so that this PQ will become the chord of contact of tangents. So that is xx1 by a square plus y1 by b square is equal to 1. So we have this one. This is the equation of PQ. So you are homogenizing the equation of the ellipse with the help of this. So you collect the terms containing x square, terms containing y square, and then xy term. We are not bothered about this. So because PQ subtends right angle at the center, coefficient of x square plus coefficient of y square will be 0. So this is your coefficient of x square, this is your coefficient of y square, and then rewriting, and by dropping the suffix you get the locus. Now third one, show that the conjugate lines through a focus of an ellipse are at right angles. Conjugate lines, so we are going to consider two lines, say Lx plus My plus n equal to 0, L1x plus M1y plus N1 is equal to 0. We are given that these two are conjugate lines. So this condition we have already derived, which means pole of one will lie on the other one. So using that only we get the condition for two lines to be conjugate lines. So this is done already. So we are taking this one here for granted. Since they are conjugate lines, you have this equation. But you're also given that the lines pass through a focus. So that focus, two foci that we have, but here we should consider that passing through the focus a, 0. So you have this. From these two equation you will get nn1 is equal to this. Now substituting the value of nn1 in 1 in this equation, you get this, and then you collect the terms containing ll1, so that you have a square into 1 minus e square. Because it is an ellipse, it is 1 minus e square, and that is along with this is e square, and already you have this. So cancel out p, which is non-zero, you have this. Rewriting this, we can have the product of these two to be equal to -1, but these two are nothing but the slopes of this line and this line. So because the slope is -1, we conclude that the lines are at right angles. So some 7 problems that we have in this exercise 36. The first one is to obtain the condition that the pole of this with respect to this may be on the ellipse. So for a general ellipse, x square by a square plus standard form, y square by b square is equal to 1, we know that minus la square by n minus lb square by n are the coordinates of the pole. And comparing this with Lx plus My plus n equal to 0, we conclude that n is equal to -1. And therefore the pole of this will be, so here n is equal to -1, so this becomes plus La square, and this becomes plus mb square, and this pole lies on this is, by assuming that we'll have to arrive at the condition. So we are substituting, and the condition is obtained. Now something similar to this we have already discussed. Show that the locus of pole with respect to an ellipse of any tangent to the auxiliary circle is. So we need to find the locus of poles, which means polar is to be considered, and what is given above, because when we want to find the locus, some condition will be given. The condition given is the polar touches auxiliary circle. So the given, the known polar equation with respect to the ellipse is written first, and rewrite that in the form y is equal to mx plus c. Rewrite that in the form y is equal to mx plus c, and from which m and c can be easily identified and written. And since one is tangent to the auxiliary circle, so the condition is c square is equal to a square into 1 plus m square. You know the values of c, m, just substitute and you will arrive at this. And to bring it to the standard form, we are dividing throughout by a power 4, b power 4, so that here 1 by a square, and here 1 by b power 4, and here a power 4. Then therefore the locus of p of x1, y, just drop the suffix and get the locus. Next one is show that the locus of poles of tangents to the circle, some circle is given, but here we notice that the center is not 0, 0 as in the previous case. In the case of auxiliary circle, we had the center to be 0, 0. So if that is the case only, the condition will be like this. If that is not like that, then the technique to be used is You have a circle. You have a circle, and its center is h comma k. Its center is h comma k, and you are considering a point polar of, let x1 y1 be the pole uh, with respect to this, then it's polar, right? So we have the polar to be a line. See that we have an ellipse. We have an ellipse, and we have a point P of x1 y1, and that is our pole. So that the polar will be, say, something like this, and what is given as this touches this circle. So for this pole you have polar, and that polar, what does it do? It touches the circle. So when it touches the circle, if we have r to be the radius of the circle, then the perpendicular distance of this point hk to this line, what is the equation of line? This is with respect to ellipse here, with respect to ellipse, so not parabola, with respect to ellipse that we need to consider. So something like this, that we have a card. I can have P of x1 y1, P of x1 y1, card passing through that, and tangents. So all that you get. So imagine that this is the polar of that point, and it touches this. So the perpendicular distance from hk to this line, what is the equation of line? Y1 xx1 by a square plus y1 by b square is equal to 1. So perpendicular distance from hk means you have hx1 by a square plus ky1 by b square minus 1 is equal to, divided by root of x1 square by whatever you have here, the coefficient, that the whole square. Similarly, this the whole square, and that is nothing but the perpendicular. That is nothing but the radius. So you have this squaring, cross multiplying, dropping the suffix, you get the locus. Next is similar to the previous one. Find the locus of pole with respect to an ellipse of a straight line which touches the circle described on the minor axis of the ellipse's diameter. So there we had x square plus y square is equal to a square. Here you have x square plus y square is equal to b square. So that is the only difference. Otherwise the procedure is the same. Next is find the locus of poles with respect to the ellipse of tangents to the parabola. So polar with respect to ellipse meaning, so xx1 by a square plus y1 by b square equal to 1 you need to consider, and that touches the parabola y square is equal to 4px. So if it is y square is equal to 4ax, c is equal to a by m, and here it is c is equal to p by m. So you know what is c from this. Rewriting that in the form y is equal to mx plus c. We know what is m, and of course what is c also. So substituting c is in the place of c is equal to p by m, and then dropping the suffix we get the locus. So that is the fifth one. And sixth one is chords of the ellipse touch the parabola a y square plus 2b square x is equal to 0. Prove that the locus of the poles is the parabola. So chords of the ellipse touch the parabola. What kind of chord it is? Chords of the ellipse x square by a square plus y square by b square is equal to 1, that touches. Okay, now we have got two equations of which one is parabola. So we'll have to write that in the standard form, y square is equal to 4ax. So when we do so, we get our a to be minus b square by 2a. We are given the parabola to be like this, but only if it is in the form y square is equal to 4ax, by considering c is equal to capital A by m, we can get the required result. So for that only we rewrite the given equation in the form y square is equal to 4ax. Now having got this, the polar, right, polar we need to consider, that's with respect to the ellipse. and that is rewritten as y is equal to mx plus c, and therefore by using the condition c is equal to a by m. So we get an equation of this form, and then rewriting and dropping the suffix we get again parabola. So locus of p of x1 y1 is this. The next one, show that the locus of fold of any tangent to the ellipse with respect to the auxiliary circle is similar concentric ellipse whose major axis is at the angles to that of the original ellipse. So it is at right angle. Major axis is at similar concentric. Okay. So locus of folds of any tangent to the ellipse with respect to the auxiliary circle. So polar with respect to the auxiliary circle is to be considered. Pole with respect to this foot comes, then you have to associate dipolar only with respect to that. So we have got that one to be like this, y is equal to mx plus c again, and here this touches the ellipse, means we'll have to have the condition to be c square is equal to a square m square plus b square. So substituting the corresponding values and then dropping the suffix, we get the locus. So next we concentrate on problems on conjugate diameters and asymptotes from hyperbola. Now the first one, tangent to the ellipse cuts the circle, so that is a direct circle, x square plus y square is equal to a square plus b square in points p and q. Prove that CP and CQ are along the conjugate semi-diameters of the ellipse, where C is the center of the circle. So here we have got one director circle, and we have got the standard ellipse. What is given is a tangent to the ellipse. Tangent to the ellipse, this one cuts the circle. So the outer one is your circle. This is your circle, and this one is your ellipse. This one is your ellipse. So what is now by keep on reading the question again and again, you will know what is what, and the diagram will come out correctly. So the equation of the ellipse is this one, and the equation of the director circle is this. Equation of the tangent at theta on the ellipse. So this one is the tangent, and so any point on that, a cos theta b sin theta. So x by a cos theta plus y by b sin theta is equal to 1 is the equation of PQ. Now because PQ meets the circle NP and Q, CP and CQ will give the combined equation, and we want to show that the angle between them is 90 degrees. So if we can show that coefficient of no, we shall check, right? The equation of the tangent at theta on the ellipse is this, x by a cos theta. Now what we are going to do is, if we want to get the combined equation, we have to homogenize the circle with the help of this line, right? So that is what is done here, x cos theta plus y by b sin theta the whole square, and then collect the coefficient of x square, collect the coefficient of y square, and the other term we are not bothered the xy term. So from here product of the roots we consider, and these things when on simplification will cancel out, leaving just b square by a square, just leaving b square by a square. So CP and CQ are conjugate semi-diameters. We know that two lines will be conjugate diameters. So if the product gives us minus b square by a square, if the product gives minus b square by a square, then you have this. Now the next one, find the locus of point of intersection of normals at 2 points on an ellipse which are extremities of conjugate diameters. So let us see again. Find the locus of point of intersection of normals at 2 points on an ellipse, which are extremities of conjugate diameters. So um, let P and D be the extremities of a pair of conjugate diameters. So the ellipse, let P and D be the points A cos theta, B sin theta. This is known to us already. Minus A sin theta, because it is sometimes we will take it as P and Q. Here it is taken as P and D. That doesn't matter. The equation of the normal at P and Q, we can write AX by cos theta minus by by sin theta is equal to A square minus B square. And the other one, for the other one, it is minus Ax by sin theta minus By by cos theta equal to this. So adding the two, you get X by cos theta plus By by sin theta equal to something. Now we also have cos theta. From here I will find, you get cos theta to be this, sin theta to be this, and then squaring and adding, you will get the locus by dropping the suffix. So next is, if CP and CD are two semi-conjugate diameters of an ellipse, then prove that the line PD touches the ellipse. So such types of problems, very simple, and they can be asked in the exam. Let the eccentric angle of P and Q be this one, that theta and 90 plus theta. Then equation of the hard PQ is, so we have the C, P and D. So if this angle is taken as theta, we know very well that the next one is pi by 2 plus theta. Pi by 2 plus theta. So let the eccentric angle of this, then the eccentric angle of D is this, the equation of the chord PD. So if I consider this, so this is a chord in a given ellipse, namely here it is taken as PQ. Now we know that the chord joining 2 points is given by x by a cos of theta plus phi, had it been phi, by 2 plus y by b sin theta plus phi by 2. It is actually so this print mistake, it should be phi. So this is the equation of the chord joining P and Q, chord PQ. So the equation of that in plus 2 itself you should have studied. Only from that we can easily get the equation of the tangent. So x by a cos of theta plus phi by 2 plus y by b sin theta plus phi by 2 is equal to cos of theta minus phi by 2. This is the equation, and we know that one is theta, the other one is phi by 2 plus theta. We just substitute that, and then this is what we get. We can cancel out one theta, so we are left with cos phi by 4, which is 1 by root 2. And so we, for the sake of convenience, what we do is we divide throughout by 1 by root 2, so that this will be a by root 2. Take it as some capital A, and the other one the same way, you can b by root 2, take it as capital B, so that you will have that in this form. So in this, okay, now we have got the equation of PQ. Now go back to the problem, what we are trying to prove. We are asked to show that the line PD touches the ellipse. We are asked to show that the PD, what you have obtained, this one touches the ellipse x square by a square plus y square by b square is equal to half. Right, now if you compare this equation with this, x square by a square, because this half comes now, so this is what you have. This straight line touches the ellipse this. So where from that we get it? See, we know that the standard form see, in general, when I am given x square by a square, see this we have already arrived at. But what is known to us, x square by a square plus y square by b square, if that is the equation of ellipse, then the equation of the tangent is given by x by a cos theta at theta. X by a cos theta plus y by b sin theta is equal to 1. Y by b sin theta is equal to 1. So if you compare this equation with this, we have taken phi to be theta plus pi by 4. So this is what we have. So this is in this form. If any equation is of this form, with regard to this ellipse, whatever I have here, that comes here. Whatever here I have here. So this one will be tangent. So in this case, we have this. So naturally, it will be a tangent to the ellipse. You have x square by a square at phi. But what is phi? Phi is again a point. We are asked to show that PD touches the ellipse. So phi is a point on this one. Phi is a point on this one, right? So that is cos phi, a cos phi, b sin phi. So it is the equation of the tangent to that ellipse, at which point a cos phi, b sin phi. A cos phi, b sin phi. So it is in that form. So we easily conclude that this PD touches. So the technique varies here. So understand the technique, because in other cases, polar and then some line, not only polar. So some line and that touches another curve. So both will be this. You can determine the line equation. You can determine, and it is tangent to what, that will be given in the problem. But here in this problem, it is not given so. You are asked to show that PD touches the ellipse. So what you do is, you obtain the equation of PD and bring it to the standard form of a tangent to some ellipse, and from the way in which it is written, we are able to conclude that, because we just compare, this is known to us, we just compare this with that and then conclude that this line has to touch the ellipse x square by capital A square plus y square by capital B square at a cos phi b sin phi. So you will have to just replace capital A by root 2 and this one. So this is what you have. So it is different whenever a problem is different, and important means you put this. If it is different means put 1 star, so that you will pay extra attention when you do that particular or when you just go through that particular problem. Now the next one is a tangent to the ellipse x square by a square plus y square by b square equal to 1, whose center is C, meets the circle x square plus y square is equal to a square plus b square at q and q dash. So that CQ and CQ dash are conjugate diameters of the ellipse. Right. Now a tangent to this, any tangent to this we have, like in the case of parabola, y is equal to mx plus a by m is the equation of tangent. In the case of ellipse, we have y is equal to mx plus root of a square m square plus b square. And C is the center of the ellipse. So what is given? This tangent, a tangent to the ellipse meets the circle. So I have got a circle director circle. Center is 0, 0. Center is 0, 0, and of course radius is root of a square plus b square. So we have any tangent to the ellipse, so something like this, this is supposed to touch. So this is the equation of this line. So what we do is, we want to get a tangent to, a tangent, this is not the figure. So you need to have ellipse, you need to have an ellipse. You need to have an ellipse, a tangent to the ellipse. This is center of this is taken as C. So a tangent to this meets the director circle at Q and Q dash. This point is Q and this point is Q dash. So what you are trying to prove this is CQ and CQ dash are conjugate diameters. So if you are able to get the product of their slopes is minus b square by a square, then we are done. So how to approach the problem? See, in order to get the combined, see, this is the idea. You have ellipse and you consider the tangent and let the tangent meet the director circle at Q and Q dash, so that you will get CQ and CP. If you can get the combined equation of this, then you will have a homogeneous equation in x and y. So it will be something like this: ax square plus 2hxy plus by square. So from which you can obtain the product of the slopes plus by square. So from this you can get the once it is homogenized, you will get combined equation from which the product of the slopes m1 and m2 can be obtained, and if you are able to show that that is minus b square by a square, then the problem will follow. So what is homogenized? The director circle is homogenized with the help of what? With the help of the tangent. Tangent to the ellipse. So the tangent to the ellipse we have taken as this. So with the help of this we are going to homogenize. So how it is done? X square plus y square is equal to a square plus b square into 1 square. And that 1 is replaced by y minus mx divided by root of a square m square plus b square. So this one is rewritten as, so that you will get 1 is equal to. And this part you must notice that it is written as a square plus b square into 1 square. So then you collect the terms containing x square, collect the term containing y square and xy term. So for convenience sake, you can further simplify this and you rewrite in the form. Again, x square is there, y square is there, xy terms are there. Now if the individual equation CP and CQ, we have got the combined equation. If the product of the slopes means, if m1 and m2 are roots of this equation, then product of the slopes is minus b square by a square. m1 and m2 is equal to this. So from which we can easily conclude that these two lines are conjugate diameters. So these are the problems. Find the coordinates of the ends of the diameter of the ellipse, which is conjugate to such types of problems already we have discussed. So that is not worked out. The third one we will do, fourth one, then sixth, and the last. So find the length of the semi-diameter of the ellipse conjugate to the diameter whose equation is. Such type of problems can be asked in section A, sometimes, or section B. Now we have already derived that the length of the semi-diameter conjugate to CP is given by CD is equal to root of A square sin square plus B square cos square theta. Now equation of CP is y is equal to 3x, that is given. Now the slope of this is B by A sin theta by cos theta. So you have this, so that slope of this is equal to uh, uh, B sin theta by A cos theta. B sin theta by, this is B sin theta slope of CP, difference between y coordinates divided by difference between x coordinates. So that is what you have. So from here what we get is cross multiplying 3a by b is equal to tan theta. Now this is nothing but sin theta by cos theta. So whenever this is given, it's quite natural to consider this right angle triangle and mark the sides correctly, and you can use this if this is B and this is 3a, then root of, so the length of the hypotenuse we can easily get. So sin theta, from the diagram, sin theta is 3a by root and cos is b by this. So that is what is done here. So therefore CD, what you need to do, you'll have to substitute. Either substitute பண்ணி simplify பண்ணோம்னா we will get this. Then the next one, if x cos alpha plus y sin alpha is a chord joining the ends of conjugate semi-diameters, we are asked to show something, right? So you have an ellipse and you have the center to be, say, C, right? And x cos alpha plus y sin alpha equal to P is a chord joining the ends of, so we shall consider conjugate semi-diameters. Just consider the ends of the semi-conjugate diameters. Suppose I take them as, say, P and D, then we can easily write out the equation of P, which is done already. So this is P, means this is P of theta, means this is 90 plus theta. So x by a cos of theta plus y by 2 plus y by b sin theta plus y by 2 is equal to, so cos theta minus 5 by 2, that is used here. So instead of 5 you have theta plus pi by 2, this is what we have. And then that's further simplified, again further simplified, so that you can have x by capital A cos phi plus y by capital B sin phi is equal to 1, where AB and theta, the relation between theta and phi are also given. Now we are given that x cos alpha plus y sin alpha equal to P to be a line, and another one is this. But it represents the same line, and therefore we can identify the two equations, so that you have cos alpha by cos phi by A equal to, and so on. So from this you get cos phi and you get what is sin phi. So that cos square alpha plus sin square, cos square phi plus sin square phi is equal to 1 is known. So that is what is done here, and it is not a locus problem. So understand each and every form of the technique of each and every problem that we do. Now through the foci of an ellipse, perpendiculars are drawn to a pair of conjugate diameters of an ellipse. Prove that they meet on a concentric ellipse. So the dotted one is the concentric ellipse. So this is what we are trying to prove, that P of A cos theta B sin theta at one point. Another one D is consider AE comma 0 minus AE comma 0, that also we consider. We consider the slope of CD, we have got it, and slope of slope of CD as well as B cos theta A minus A sin theta. So the first one. Similarly, the slope of CP can be obtained, and that is given by minus A by B cot theta. The first one is A by B tan theta, and this is this. Now let the perpendiculars from the focus C, that is P. Okay, we should take S itself. Is y minus 0. I know a point, and I know the slope, so I can easily write out the equation of ST. Here is S and here is T. So that we can that can be easily written. Now let the perpendiculars from the focus to CP and CD meet at T of x1, y1. Let the perpendiculars from the focus so let the perpendiculars from this from foci to CP and then meet at T. So this is what we have done, the locus of which only we are trying to find, right? So similarly, the equation of S dash T is, so in the same way you consider this T of x1 y1 lies in both. So you have this, then we'll have to simplify this further and bring it to the standard form so that you can tell that it's a concentric ellipse. So what is the meaning of concentric ellipse? The center of this as well as the center of this will be the same. So such ellipse is called a concentric ellipse. If P and D are extremities of conjugate diameters of the ellipse, show that. So there are three subdivisions, at least one subdivision can be asked in the exam. So for the first one, P and D are extremities of conjugate diameters of an ellipse. So that is standard. So that is given to you. Which ones? P and D. E and D. Right. So the first one, locus of middle point of P, D. So the midpoint of this is something. So how it is proceeded? If x1, y1 is the midpoint of PD, then x1 is equal to, you want one to be A cos theta, the other one to be minus A sin theta, one to be B cos theta, the other one to be, B sin theta, the other one to be B cos theta. So we have the coordinates of the midpoint to be this. So x1 is equal to this, y1 is equal to the equation of the locus is found by eliminating theta from 1 and 2. By eliminating theta from 1 and 2, you get this. Okay, this is further simplified as this. So squaring 3 and 4 and adding, we get this. So this one. We need to get rid of this cross term, so automatically that will go by squaring and adding. And therefore the locus you can easily find. Now the eccentric angles of P and D are theta and pi by 2 plus theta. The second one, the locus of feet of the perpendiculars on PD from the center of the ellipse. The locus of foot of perpendicular on PD from the center. Center, it is something. Right. So how it is done? The eccentric angles of P and D, okay, the equation of the line joining, yes. The equation of the line perpendicular to the line PD passing through the center. So the equation of the perpendicular to the line PD equation already you have, from which you can easily obtain the slope, and you can easily get the equation of the line perpendicular to the line PD. So this is what we have. Now if x1, y1 is the foot of the perpendicular from C to PD, then it has to lie on the equation. So you have this. So from this, what is sine and cos also you will get. but that could be discussed later. Now substituting this in 1, we get this. So you have we'll have to drop the suffix to get the locus. So the third subdivision, the tangents at P and D are the locus of point intersection of the tangents at B and D. So you write out the equation of the locus at P and the equation of the tangents at P and D. So you have this. Now at the intersecting point of the two tangents in the formula let it intersect at the point x1 y1, then x1 by a cos theta, it will lie on the line, so it will have to satisfy the equation. So you have this, and then you will have to eliminate theta, then you get this. So this is also an important problem. Next one is given as homework, and in this you'll have to make use of the concepts in conjugate hyperbola, that is given by C is equal to 2a minus h. So it is this that should be used. If you haven't used, then you will not get the answer. So these problems can be easily done.